Okay, this is a video on relativistic length contraction for Physics 1000 at Auburn University. So this problem is set up the same way as the previous video on time dilation. If you haven't watched that one, I would encourage you to watch that one first. But the setup is the same. There's a rocket traveling at 0.8 c, that's 80% the speed of light, compared to a stationary observer. So your stationary observer is here. And in the last video we cared about how our clocks were running. In this video we care about what our rulers look like. So let me make that a little clearer. We know that not only does time run differently in the two frames of reference, it's that the stationary observer will perceive dimensions, distances differently as he looks at the moving frame of reference with respect to himself. So we, once again, there's a distance measured in the frame of reference, which is called the proper length. And I'm going to call that L naught, proper length. In other words, if I'm an astronaut on this rocket ship, and I take a ruler and I measure this rocket ship, I measure L naught, I measure the proper length. But if I'm comparing that rocket ship to a ruler that I'm holding, me being the stationary observer now, what I'm going to find is that I measure a different value. I measure L. So I guess I shouldn't have said that I was the astronaut and the observer. Let me be a little more clear. For the astronaut on the ship, he takes his ruler and he measures how long his ship is, and what he comes up with is this proper length L naught. For me, standing still on the ground, watching the ship go by, I compare it to a ruler that I have in my hands, and I measure L. I measure a different value. And we have a formula that relates these two, which is this. L, the length I measure, corresponds to the proper length, the length the astronaut measures, over gamma. This is, over gamma. This is similar to the time dilation formula, although you remember in that instance it was T that I measure equals T the astronaut measures times gamma. In this case, the length I measure is the proper length, L naught, divided by gamma. So the steps to solving that are exactly the same. If I'm given that I measure 100 meters, what I'm interested in is what distance the astronaut measures. So I measure the ship as it's moving. I find it's 100 meters long, and I'm curious what the astronaut on that ship measures his ship to be, because it will be different. So I need to solve this equation. Just like I did before, I'm going to solve this equation for the unknown. What I know is L. I'm given what I measure, and I know gamma because I know how fast I'm going. And if I solve that, I just get the proper length, which is what I care about, what I want to know, is equal to L, the length I measure, times gamma, this relativistic factor. Let me go to the next page and write that down. What I get is L naught is equal to L times gamma. And I've just rewritten the formula for gamma here above. It's the square root of 1 over 1 minus v squared over c squared. And I've already solved this. I solved this in the last video because I'm going the exact same speed. Let me just give you a recap on that. This is exactly the same frame from the last video. If v is expressed in terms of c, as it is here, then all I have to do is square it. So I square the 0.8, I square the c, and I plug it in. My c squareds handily go away. This is why we want our velocities expressed as a fraction of the speed of light. My c squareds go away, and I'm just left with this pure number, which in this case, for traveling 0.8 the speed of light, happens to be 1.67. So now I'm going to go back, and I'm going to plug in what I know. I know that L is 100 meters. That's what I measure this thing to be, times 1.67. Notice I'm multiplying by a number bigger than 1, which means the astronaut perceives that his ship is bigger than I do. He measures in his reference frame, and what he comes up with, if you plug these numbers into your calculator, it's not that hard to do, you come up with 167 meters. So he thinks his ship is 167 meters, and as I measure 100 meters. Notice it has contracted. This is why we call it length contraction. I perceive his ship being smaller than he does, just like I perceive his time running slower than he does. This is a consequence of the fact that time and space are intimately and inextricably connected.